Hi, so this is a quick little video just to show the data model that's used within StackTach and to illustrate some of the use cases that we have and hopefully to start a discussion about how we can get that same sort of functionality with the data model that's inside of Ceilometer. The big thing for us is that we have a lot of users hitting the StackTach database. We've got a lot of data in there. Right now, we've got over 10 million records, which reflects over 90 days of data, and that's the full notification that's coming out of OpenStack. So that's across multiple cells, multiple deployments, multiple data centers, and the entire notification is kept. So the raw JSON payload, it's highly indexed on the fields that are important to us. So what I'll do in this video is walk through the data model, and then I'll walk through some of the queries that we're performing so you can get some sort of indication of what we're going to need to be able to get out of the Ceilometer data model. I'll start off with this little diagram here. So this is basically what the data model looks like. We have the raw data table, which is the notification as it comes in, and it's denormalized. So we've got a column for all of the important fields that we need. So that would include things like the instance ID, the request ID, the tenant ID, the start and end times, or well, the start time, I should say, just the time of the event that came in, the data center that it was deployed to, the server that it occurred on, or the host, the event name. There's a lot of really important information that we want to be able to jump around on from the raw notification itself. And so to keep that denormalized and keep that in one place really helps keep the queries simple. But from there, we want to add value to that raw data. So there's other operations that we do on top of that to produce some more meaningful data tables. So one that we have is a set of master detail tables. The master being this life cycle table, which basically just contains the instance UUID in it, and that becomes the main connection to this timings table. And the timings table is a link to the event, which would be the .start raw data event and the .end raw data event. So let's say we get an event called compute instance resize start, and then compute instance resize end. Then what we do is we would create a single lifecycle record for that UUID the first time we see it, and then every time we see a .start and a .end with the same request ID and with the same event name, we would create a new timings record for it. And they would just link back to the raw data table to say, this is the, if you want all the gory details, you can go back to the raw data table to get it. But otherwise, in here, we store the time delta. So we say this operation took us this long. And that means that later on, when we want to do some more interesting queries, we don't have to go back to the raw data table all the time and try and find the .start and the .end and do a complicated query there. We have a higher level one here that we can get it from. Likewise, when we want to say, show us everything around this instance ID, around UUID 1234, we have a very simple place that we can go and say, here's all the operations that came through. And we can search on, by request ID or whatever to find that. Or same thing with the raw data. Request ID is a great one because we'll have a request ID that follows through for the entire from the API call all the way through, so we can see what happened to this call. So for debugging OpenStack, that's a very powerful query. But for service level agreements, it gets a little trickier. For service level agreements, we want to find out how long things took. So we want to find out the time from the API call all the way down to when the service last fulfilled it. So the request tracker is a new table which stores that information. So it's based on the request ID, and we start the clock when the API call first comes in. So when it hits the API node, that's when we store it. And then we track every .end event that comes through with the same request ID, and then we store the time delta in this table, we update this record for that time delta. So now we can say, okay, so we're seeing that resize operations take this long on average. We see that run instance operations take this long on average. And we can see it from the end user's perspective. This call took forever, or this one was very fast, so what's going on there? So this is handy information. I'll just show you how that looks in the code here. This is the StackTach code. This is a Django ORM, so it's a little bit different than SQL Alchemy. But so some of the fields that we track in the raw data, the routing key, the state, this is really handy information too, the state, the last known state. So these are all the compute instance update events that come through. So we can see, show me all the things that are in a resize state, or all the things that are currently in a power off state or something like that, which is handy. Who published the event, what was the event, which server and host did it come from, the request ID, and like I say, the raw JSON event. So the reason that we store the raw JSON data is there's a lot of information in there, and to lose that information would be like taking a photograph of a steak dinner. You're losing all the nutritional value. Down the road, especially where we're storing 90+ days of this stuff, and even longer. Ideally, we'd like to be able to store a year of it for analytics. So when other departments and other groups want to get at this information, even though we're not using it today, we do have to store the full fidelity of the notification. There's a lot of good stuff in there. The lifecycle table, which I told you about, and the related timing table, basically just says here's the UUID, here's the last known state it was in, and here's the last raw event we saw for this UUID. So that's just, really it's the instance ID that we're most interested in. These are just sort of nice to haves, just to make things a little bit faster. We could probably even drop those. But really the timing stuff is the thing that's interesting. So what's the name? The name of the event, and you drop off the .end and .start parts of it. So it'll be compute instance, run instance, for example. You wouldn't see the .start and the .end parts. What's the lifecycle record that we're interested in? Again, these are the foreign keys here. So the raw event that started it, the raw event that ended it, and then we store the start and end and the diff times for it. And you'll notice that these are stored as decimal fields, not as date times, because this will work with most any SQL database, because it'll allow millisecond or actually microsecond timing. So that table's pretty straightforward. And then we get into the request tracker, and that one's even simpler. You see that as we start to move further and further away from the raw data table, the other tables get quite small because they're just adding little bits of value on top of it. So we've got the request ID, what's the life cycle that we're interested in, the last timing that we saw. So this is pointing to the last timing record that we saw, right? So this data has already been computed for us. What was the start time, and how long have we gone past? How long have we gone so far on this operation? So these are 3-4 simple little tables. If you look at how the worker deals with this stuff, in a previous video I showed that the call will come in from the worker and it will store this information in the database, and that's basically what we're seeing here. Process raw data is the call that the agent will initiate to say, here's some data, some raw data, and I want you to store it. So this stuff here is just parsing it out, and then we store a raw data record in the database. The next stage of it is to take that and to look at it a little closer so we can aggregate it and roll it up into our life cycle and timings table. Now, this is all done in one worker, and this is the reason that we don't want to really push on with StackTach anymore. We want to change the architecture to be a more tiered and pipelined processing mechanism. And we want to make it more plugin driven so that other people can hook in their own pieces into the model here. So we think we've got some good ideas on how to do that. But here's the way that this works anyway, just to give you some indication. So once we've processed the raw data, then we call aggregate. And aggregate is the method that's going to deal with creating the life cycle and the timings table. So now we're going to look for a .start and a .end. So if we haven't seen this UUID before, then we're going to create a new lifecycle. We do a query, and if we haven't seen it, then we'll create a new one. We're going to update the last known state and the task for it, and we save that lifecycle record. Then we've got, is this a dot start or a dot end operation? We'll get into this KPI tracking piece in a little bit, so let's ignore that. So if it's not a dot start or a dot end, then bail out, basically. And then we get into the actual timing operation. So now we're looking for what's the timing record that we're dealing with, and then if we've got it, then compute the difference in time and store that. So that's going to get the life cycle and the timings table freshened up and kept up to date. The last piece that I mentioned is the request tracker. And the request tracker, like I said, is the one that tracks the time from the API right down to the last service that did something meaningful. And it leverages off of this aggregate operation. So it says if it's not a dot start and a dot end, then this is probably a call that came in from the API. And we're going to start our KPI tracking. Well, and I call it KPI. It's a resort, so KPI is key performance indicator. But this is actually the resource tracker. So this, now we're starting off, say, okay, this is not a compute instance update, so we're not interested in it. It didn't come from an API, but otherwise we're going to create a resource tracker and we're going to store all this information. And then every time that we get a completed aggregation call, so now we've got a dot end and we've got a diff on our timing record, we're going to use that timing record to update our KPI records. So we know the life cycle, we know the timing record, and here's the raw event that generated it, and we'll go up to update KPI. And update KPI will look at the request tracker, search by the request ID. This is one we weren't tracking, so bail out. Otherwise, update the timings, update the duration, and save our tracker. So very simple. But the purpose of this is to illustrate that from one little piece of data, we want to take that and leverage off that and build new pieces of data, new columns, new database, new tables, new resources that we can use for our metrics and our monitoring. So this works in a very trivial case. Obviously, if this got more complicated or had to do more complex queries, it wouldn't scale properly because we'd be pounding the database every time we read an event. And the most important thing is to get those events out of production OpenStack as quickly as possible. We don't want to let that production rabbit queue grow to get to a point where it starts to become an issue. We want to flush that out of there as quickly as possible. So there is a proposal in Ceilometer right now for multi-publisher, and well, I won't get into that right now. What I will talk about right now is how can we have a flexible data model, like something a little richer than, or more flexible than the one that I just showed you with the life cycle table and the timings table, but something that people can extend and they can add their own hooks in there. So with multi-publisher coming in, people are going to want to be able to create their own data and things. So one of the proposals on the table is to do this. Right now we have a meter table inside of Ceilometer which stores the main information, and there's a primitive metadata table that's or a metadata column that's associated with it. It says here's the metadata, and it's basically just a JSON field inside there now. But obviously that's not going to work very well for complex queries. There is a proposal for something called dimensions, which is essentially just a key value pair. And what we would have to do is have this metadata table highly indexed on the key, maybe even on the value. No, probably on the key, so that we can query the metadata table and then find the set of metrics that are related to it, because every new column or new table like we've added in StackTach would have to become a new meter inside of Ceilometer. So our lifecycle table would have to become a new timing meter with metadata on it that says here is the UUID that we're interested in. So we would have a key of instance UUID, and then the value would be the UUID we're interested in, and that would tie off to a new meter. The question with this is how well is that going to scale once we get up to, well, like I said, for 90 days of data, we're seeing about over 10 to 12 million records right now. We're going to see a lot more records if we go to this highly denormalized model, or highly normalized model, I should say. So how well is a SQL database table, or how well is a MongoDB table or something going to perform with that sort of a query and load, especially in the Mongo sense with a sharded database. So I think that's probably the next step, is to see, will this model work for that. So that's really a discussion of that part. I'll show you a little bit also on how we use some of these tables to get some queries. So from here, this is a file called Stacky Server. It's part of StackTach. It's basically the command line tool for pulling out some interesting metrics out of here. And most of the stuff is pretty straightforward, right? It's show me the events, show me the deployments, show me the hosts that are out there, show me everything around a UUID. So this is basically just a query right off the raw data table that says, show me everything around that UUID, ordered by when. So that's pretty simple. But then we get down into the fun stuff. Timings are a little bit more interesting. So show me everything, all the timings for a particular name that has a start and an end, and then order it by the time it took. So that'll give you a query that says, here's all the operations that we're seeing inside of OpenStack, ordered by that have completed, and they're ordered by the time they took. So you can find the outliers very easy. The odd delete that took 2 days for it to perform. The summary report is another handy one. This one goes through and it says, here's all the timings that has an actual timing associated with it, and then we're just going to get a summary of so the min, max, and average of all those operations. So you can see across the board how long a run instance is taking. Here's the low end, here's the high end, and here's the average time it's taking. And it'll tell you how many of these we've seen. So we might have seen 5,000 run instances over the last month or so. The request information is says, show me everything around a particular request ID, which is kind of handy. Show and watch. Show is just given more details on something. Watch allows you to do. Watch is a really powerful debugging tool within StackTach, which allows you to, from the command line, do like a tail -f on all the notifications that are coming out of StackTach. So that has some interesting queries in there as well. It's mostly just looking at the raw data table though. But the KPI one here is a really interesting one. So this one is going through and pulling out all the request trackers over the last 24 hours that actually have a timing. And it's showing, here's all the things that took a really long time. So we can look at this and say, we've got a problem in production. These operations are taking way too long. What are we going to do about it? So these are very simple looking queries, but in order to make them simple queries, we had to have a rich data model to support it. Anyway, that's all I wanted to talk about with this. Thanks very much.